This tutorial is for problems involving objects sliding down inclined planes where you have no friction. And so let's say you have an inclined plane at some angle theta, and an object which you're going to represent by a point is sliding down with some acceleration. So the net force acting on this object is going to be down this inclined plane. To find that net force and the net acceleration, we have to figure out what all the forces acting on this object are. So in this case, the first force we have to consider is the force due to gravity. So the weight of this object acting downwards, which is equal to m times g. And the second force we have to consider is the normal force, which is going to be perpendicular to the interface between the object and the surface of the inclined plane. So we call that Fn, which acts 90 degrees to this inclined plane. So to find the net force, we have to find the x and y components of the weight and the normal force and sum them up separately to find the x and y components of this net force acting on the object. The easiest way to do this is to redefine our x and y directions. So in this problem, we're going to consider the x-axis to be parallel to this inclined plane, the positive x, and the positive y direction to be perpendicular to the inclined plane. So we're going to draw our free body diagram. Using this new definition of our x-axis. And our y-axis. So positive y goes this way and negative y goes that way. And we'll draw our object in the center here. Alright, so the first force we'll consider here is the normal force, which acts parallel to the y-axis. So the normal force acts this way. And the second force which acts on this object, again on this diagram, is the weight of the object. So that will be acting still downwards relative to the earth. So that's W. And so if this angle is theta, we expect this angle here to be 90 minus theta. So the angle here is 90 minus theta. And so this W, the weight here will have components acting along the x-axis and the y-axis. And so we'll simplify that by, so we have a component going down this way along the negative y-axis and a component parallel to the inclined plane. So this is a 90 degree, and we have our x component here and our y component acting in the negative y direction. So if this angle here is 90 minus theta, then the angle here is going to be theta, since we have a 90 degree total angle here. So we can find the x and y components using the Socrates rules. So Wx is equal to W times the sine of theta. And the y component, Wy, or the magnitude of the y component, so let's look at magnitudes, is equal to W times the cosine of theta. So whenever you're breaking things up into components, you need to draw a diagram to give you the correct sines and cosines in these kinds of problems. Alright, so to find the net force acting along the y direction, we're going to use Newton's second law, which says the net force has to be equal to the mass times the acceleration in the y direction. And so in this problem, the object is not accelerating along this direction, it's only accelerating along this direction. So this AY here is equal to 0. So the forces acting along the y direction are the Fn, which is in the positive y axis, and the y component of the weight, which is acting in the negative y direction. So we'll put a minus sign over there. And that has to be equal to 0, since the acceleration in the y direction is equal to 0. So solving this out, we see that the normal force is simply going to be equal to, so this goes over here, the positive Wy, and we found the weight of the y component to be equal to the weight times the cosine of theta. So Fm, the normal force, has to be equal to mg, since the weight is mg, times the cosine of theta. Alright, now we can find the net force acting along the x direction, and that again has to be equal to the mass times the acceleration along the x direction. And so the forces acting along the x direction in this problem, since there is no friction, is only going to be Wx, right? There's no other force going anywhere, either up or down along this inclined plane except for Wx. So Wx is equal to max, and we found Wx to be the weight times the sine of theta, and it's positive because it's going down the positive x-axis. So W times the sine of theta is equal to max, and we know that the W is mg sine of theta. So if we want to solve for ax, we can divide both sides by the mass, and we see that the acceleration along the x direction is equal to g times the sine of theta.